Yes, sir. Yes, sir.
Okay, yeah. So, what I'm going to talk about is the research scope in laser-based processing. Maybe you can keep this in a quote at NIT Trichy, because what are the things that I am going to talk about for the next 1 hour or so. That is more on what we are doing using laser and what is that is possible with the laser in different aspects, more towards on the research perspective. And as Ms. Anjali indicated during this introduction, that I have done my PhD in laser surface engineering in TU Klosthal, Zellefeld. That really made me inclined towards laser-based processing, and I had a dream to establish a very good laser-related infrastructure at NIT Trichy after coming back from Germany. And I came back in 2006 after graduating from there, and in 2014 I got a first light of my dream, and we got a very first laser. Then after that, the quantum of project, which enabled us to take this process to the next level in terms of getting more funding. And as we mostly work on advanced laser processing, and that really helped us. And to the best of my possible extent, I have consolidated some of the information, what is that available in our laboratory, and some of the case example, and some related videos also, to have some better visualization of the different processes what we are doing. And I am trying to get some list of possible projects that you can explore. And the case studies itself will I can talk about a week long. Due to the limitation of time, I am just giving very crisp information about each cases. And if anyone is interested to go through further in exploring what we have done, that all available in the form of journal publication in the open literature. So with that basic introduction, this is the way I am organizing the entire presentation, as some of you might be new to the laser technology, but I am not also going to give a very detailed introduction, rather just what is laser and what are the different possible processes that we can do it with laser. And we'll start with surface engineering. There we 70% of the work that we are concentrating on, and what are the different categories in which that we are working, and laser welding, micro machining, shock peening, and finally additive manufacturing. We are also enter into additive manufacturing, and to my knowledge almost 10-15 additive manufacturing systems are there within NIT, and those are all based on either composite based or what do you say, polymer based. And even in the Siemens Center of Excellence, we have one FDM printer. I'm not going to talk about all those things, rather the metal based additive manufacturing, which primarily uses the laser system, that I will also give a brief outline close to the end of the presentation. So basically this laser, it's an acronym for light amplification by stimulated emission of radiation. And this is an electromagnetic radiation, and basically it's a light source. So with this light source, what we are going to do with that, depending upon the application, it's different. But when you look at a physicist, when he is using a laser, he'll be using for some kind of interferometry or some kind of an understanding on the light reflection, all those things. When you talk about chemists, when he wanted to use that, he'll be using on a photochemistry, how this is reacting with the chemicals, what he has prepared, to understand the stages of the processing. When you look at in some other applications, people will be using for measurement and all those aspects. But primarily in our scope, we are using the heat content available in the laser to affect different material modifications, predominantly heating the material, melting the material, or cutting the material, or doing some kind of micro machining. So basically, the high energy density available in the laser, what we are using to create different surface modifications or responses, that is our primary objective in all our applications. And in order to realize the laser light, you need to excite the atoms available in laser medium, and depending upon the medium, you need to have some kind of excitation source to excite the atoms. That's what given in the different energy level. And if you are exciting the atom will jump over to some higher energy state or some metastable state, and it cannot hold in that energy state for quite long time. It will try to come back to either the metastable state or the ground state. During that reversal, it emits a photon. So basically, the laser, it's a photonic emission. We can imagine it's this magnetic radiation is in the form of pockets of photonic emission. So that kind of emission, that is called spontaneous emission. So due to the reversal, it spontaneously emits a photon. And there is one more emission is possible. For example, if you have two atoms in the excited state and one atom hits the another excited atom, rather than emitting one photon, it emits two photons, because due to the additional heating energy, it has additional energy. And this particular case of emission, it's called stimulated emission. So because of the stimulation, you are emitting a photon. So due to this two different forms of emission, a lot of photons will get emitted, and it will allow to oscillate between in an optical cavity. That is a combination of fully reflective mirror and a partially reflective mirror. And at one point of time, when you get a population inversion, the state called, when you have more atoms in the excited state compared to the ground state, you can get a very quality beam of light source, which is enormous in use in the recent times in multiple industrial vertical. Basically, these are the important characteristics of the laser, which clearly distinguishing this particular light source in compared to other light sources like sunlight or LED light, what is coming out of it, the monochromacity, coherence, the directionality and beam divergence. These are all very important property. And why we bother about much of this light to be a monochromatic? When the light is monochromatic, then only you can get only one wavelength or a single wavelength. And most of the time, when you talk about focusability, how you are focusing the light to the very small spot, then you can get a maximum energy density possible. So for this reason, the coherency, monochromacity is very much essential when you wanted to use a high energy density processing in order to heat a diamond or melt a diamond or even vaporize the diamond. You need to have a tremendous energy, heat energy to be generated. So for that, these characteristics is very much essential, which you cannot get in some other light sources like sunlight, where even sunlight is an electromagnetic radiation, but still it has multiple wavelengths and focusability, it's a big problem. And there are quite a number of lasers available, and I am just for the sake of example, I have included few types, and the types are basically based on the medium what you are using to generate a laser source. And a solid state laser, where the medium will be a solid state like NdOg or some kind of a crystals. Gas lasers, basically you have only one laser, that is CO2 laser, and this was also invented by an Indian called Kumar Patel, and this is one of the workhorse for heavy industrial cutting. Then using semiconductor devices also you can create laser energy, like a lot of semiconductor lasers are available, like gallium arsenide, gallium aluminum arsenide, indium gallium arsenide, all those things. And using a chemical dye you can generate a laser. Even you can use a free electron laser, and chemical lasers with a sudden chemical reaction you can generate a laser energy. This is quite useful in defense industry, where you wanted to produce sudden energy release in a war front, where this chemical lasers is a very good potential for that kind of an application. And throughout the world, now they are looking at this kind of a chemical lasers for a destructive military and defense applications. You can see in many of the news feeds that it is quite interesting advancements are happening. And Excimer, it's a noble gas laser, and fiber, it's a kind of a laser. It has a very good quality. And across the wavelength chart, you have multiple lasers at different point of time. And when you're starting from even 100 nanometer, in ultraviolet, you have a lot of this noble gas-based laser. And in near infrared, you have all semiconductor and solid state laser. And in a mid infrared, you have only one laser, CO2. And surprisingly, in a visible range, there is no laser, but still in a plain eye, we are seeing some of the laser. When you look at in the laser shows, most of the laser lights are visible, and they are using a technology to amplify the wavelength to make it visible in this range. So with that basic, we look at some of the research scopes possible with a laser in different fields or different classification. And laser surface engineering is one of the application where you find laser is penetrating in an enormous manner, and in most of the functional material, improving the surface property is very much essential, more particularly the tribological property. And when you wanted to improve the service life, definitely you need to look for some kind of tribological property improvement coatings. And in that, you have multiple varieties of technology available in the open market, and which are competing each other very vigorously, because when you look at in the recent market, this kind of service life becomes one of the competing strategy. If you give a very extended service life of 10 years, 15 years, something like that, naturally the market segment could be very high. And the price sensitive market like India, you always need to look at from the perspective of reducing the cost and improving the service life, and what is the product that you can offer in a economic rate or a competitive rate that will serve for more time. That is a kind of a thing that they are looking for. Even somebody is like to pay even a higher amount when it is providing a reliable service. So for that, the tribologists and surface engineering technologists are looking for quite a lot of interesting coating methodologies and techniques. And in that, you have plasma spraying, high velocity oxy-fuel spraying, and then thin film deposition, chemical vapor deposition, physical vapor deposition, all those stuffs. And laser is one of the such technology which is equally competing. In certain cases, it is one of the unique process where other processes cannot compete on, where it is providing a very good improvement in surface property. And this is one of the process which gives the metallurgical bonding to the substrate material, which other processes cannot give. In such a way, there is a lot of interesting advancements are coming in laser based surface engineering technology. And again, the surface engineering can be brought under these three categories: surface heating, melting, and alloying or cladding. Each one has its own application domain. For example, all the iron based or a ferrous based material can be transformation hardened. If you have a iron based material, and among the different phases like austenite, ferrite, martensite phase is very high hot, and possibly if you able to precipitate those phases at high temperature, possibly at room temperature, possibly you get a improvement in hardness by several fold. And as a thumb rule, any tribological applications, if you improve the hardness, most of the problems can be addressed. And the hardness is one of the important property, but not in an erosion resistance, not in impact related contact. In rest of the cases, you get a very good improvement. So surface melting for other functional materials like titanium, nickel, magnesium, aluminum, if you melt and solidify at a very, very rapid rate, this is very much possible with the laser, as you are generating very high energy density in a very, very short duration, and then you are releasing or removing the energy very quickly in terms of a few 10 power 6 or 10 power 8 degrees centigrade per second. Such a high melting and solidification cycle possibly will lead to fine grained microstructure, high homogenization, and the generation of these kind of unique structures possibly promote a very good harness improvement. And in these two processes, we are not adding any kind of external alloying element, but in certain applications where this hardening and melting is not sufficient enough to provide an improved property, then literally you need to add some other external alloying element, like if you select some hard ceramic, if you select some kind of matrix material in order to provide a specific protection, then you need to go for either alloying or cladding. And this is a kind of a process map which is giving some information about the interaction time, then power density, and you have multiple laser based processes, and we are working on almost all processes with different types of laser. And if you look at any kind of laser based application, you may need to have some kind of feeding mechanism. When you wanted to feed the powder, you need to have an actuating mechanism to move the laser from one spot to another spot, and you need to have primarily a laser source to create the required energy to do different kinds of operation on the material. So this particular schematic gives one such kind of laser setup that I can call it as an universal setup, where you have a laser optics. This optics, it has a combination of lenses to harness the beam. Harnessing is nothing but the raw beam which is coming out of the fiber optic need to be focused to the very small spot. When you are focusing in a very small spot, then you get a very good energy. And this is the laser source, and this is the robotic arm connected to a computer where you can program the system to make a movement. So when you wanted to cut any material, normally you can place the workpiece in the focal point, and when you are keeping the workpiece in a focal point, you can get a maximum energy available with the laser. Then you can vaporize and get any kind of a cutting action. When you wanted to do some kind of a welding, possibly you can do a little away from the focal point, as your intention is not to vaporize the material, otherwise just to melt the material to realize some kind of a fusion. And if you wanted to do some kind of a surface treatment, then obviously your defocusing position will be little more, and you like to get the possible reaction if you are appropriately reducing the energy density according to the process requirement. And for any kind of alloying or cladding, and if you wanted to feed a powder, then you need this kind of a setup. It's a powder feeding arrangement, and you have a argon gas supply to provide an inert atmosphere, and a powder feeder and a nozzle. And what I have shown here, it's a lateral powder feeding system, and you can use coaxial powder feeding system also for to affect any kind of a laser cladding. And this is the system available in the laser surface engineering laboratory, and it's a 3 kilowatt fiber laser. And what you are seeing here, it's a laser source, and this is the laser head. And this particular system is quite useful to do multiple operations like surface melting, surface welding, or surface cladding. And whenever you wanted to do this kind of an operation, this is the fiber optic cable actually. So through the cable, you get energy delivered, laser delivered to the system, and using this head, the beam is directed towards the workpiece, and this will do variety of operation. And what you are seeing here, it is a surface treatment head, and what you are seeing here, it is a cutting head. And this is one cladding arrangement. We made it a customization with a single hopper, and you can see here, this is the coaxial powder feeding nozzle, and through that you can feed the powder and do the operation. So using this you can do laser surface treatment or cutting, welding, and using this you can do the cutting, and using this you can do any kind of alloying or cladding. And this is basically a 3 kilowatt fiber laser, which is a workhorse in our laboratory doing multiple operations. So far we have completed multiple industrial projects, and still we are doing a few consultancy using this particular laser source. And these are the two case example what I feel worth mentioning here. We worked on two different materials. One is to improve the erosion resistance of the induced draft blade for BHL, and this is for improving the erosion resistance of nickel based aeroturbine blade for gas turbine research establishment DRDO Bangalore. And in both the cases we are using the laser energy to modify the microstructure in order to improve the surface characteristics, little improvement in hardness. You can see here from the base microstructure we have created a kind of a fine dendritic structure, and in the case of laser surface melting of nickel based alloy, we modify the surface similar to that other laser based modification. And in both the cases you can see the hardness improvement that has been obtained up to 2 to 3 fold, and these are some of the samples what you get during erosion testing. And we also used a white light interferometer to understand how that erosion happening when the particle hits at different angle, and we try to categorize the erosion resistance. And you can look at after surface modification or laser surface treatment, the rate of erosion have come down very rapidly, and it is proven that it is possible to apply this laser surface melting process to improve the erosion resistance. So similarly, when you are trying to improve any kind of tribological property, either a wear or a cavitation or an erosion or a pitting or fretting, whatever the way you wanted to modify, either simply with the laser surface melting or with some kind of an alloying, possibly this system will be quite useful. And again, we have done an alloying on a disc brake rotor system for an automobile application, and here also we recorded a very good improvement in harness. And this one project right now ongoing, as we are doing some kind of a micro cladding in order to treat the worn out turbine blades of nickel or titanium. And this is one of the unique work what we can say, as you can look at in the open literature. So far they have done for a clad width of greater than 1 mm or 1000 micrometer, and we have successfully created less than 1 micrometer clad width that's been called as a microcladding as 990. Even in certain cases we have gone up to 700 micrometer, and here you can see it's a double layer over and above, and likewise you can have a multiple layer build a kind of technology. And this is almost similar to in a DMLD based laser additive manufacturing system, and they are using a kind of a coaxial nozzle to clad multiple layers, and you can program the system to make a movement so that you can build the component layer by layer. So this is the direct metal laser deposition basics, but when you are doing additive manufacturing, the system will be little different to do that one. Possibly even you can use our plain cladding system to build multiple layers to affect any kind of DMLD based additive manufacturing also. And this is one video what it shows when we do the laser cladding on a using inconel powder, inconel 718, and this is the coaxial cladding nozzle. You can see that through the tubes we are feeding the powder, and this is the video related to cladding using titanium 6 aluminum 4 vanadium powder, which is little problematic always. You can see the type of flame it is coming out, and you need to be very careful when you are operating this kind of systems. it's about laser cladding. And laser welding, we used our system for limited application of laser welding, and whenever any kind of requirement comes, we do. Otherwise, mostly we do on a laser surface treatment applications. And there are two types of laser welding. One is conduction limited, another one is keyhole. And this keyhole welding, where it's unique of laser welding. In other processes, you cannot establish a kind of a keyhole, and you can go with a very high aspect ratio in many of the cases. And the process parameter control based on the laser beam, shielding gas, gap tolerance, all those things are very, very important. I am not going to talk about much. And this one unique process, what we have done for GTRA again, we have a requirement of doing a dissimilar welding. Actually, this is the front portion of the blisk, that is the bladed disc, and this is the turbine shaft. And this is one engine they are working on right now, which is STFE. And here, this shaft, it is steel based, and this is the nickel based. And whenever you have a requirement of doing dissimilar welding, you get into a lot of issue in terms of cracking, stress corrosion, all those issues, because of the fact both of the physical property of the material are completely different. And whenever you get into different melting point material, different thermal expansion coefficient, thermal conductivity, it is a complete mess. So how to avoid that? By appropriately using this laser technology to weld this kind of a dissimilar material. That is the project all about. And we have done an extensive FEM simulation to understand the von Mises stress distribution after welding, and also we use the offsetting strategy to make a successful weld. And earlier we get some kind of a pores in the bottom of the welding, and finally we made a successful welding. This is the portion, and even it cleared the non-destructive testing what's been done in GTRA. And this is the blisk, and this is the shaft, and both are welded using our optimized process, and they are using this optimized process in their turbine engine. And some of the possible areas that you think about using this laser welding for hermetically sealing electronic capsules with a low heat affected zone. And the better strategy where laser welding overcomes many of the common welding process is low heat affected zone, because the energy what is diffused into the material is more concentrated. It won't get distracted very easily, and it won't get diffused into the surrounding part of the material. So possibly you get a low heat affected zone, and whenever you get a low heat affected zone, the thermal disturbance to the surrounding part of the material is very, very limited, which is very much required in many of the applications. Then end plate on a piston assembly for a car near to a nylon. And when you have a polymer material, always if you have a higher heat affected zone, there is a possibility for it to get melted, but a laser can do that one. Welding a hot pacemaker, tailored blank normally have a different material welded together, then you need to deform that. Bimetallic saw blades, repair of nuclear boiler tubes, multiple welds, strip welding, three-dimensional welding. So likewise, even you can see that it's used for fabric welding with made of thermoplastics, and it has extensive application. If you have some novel applications that need to be realized, then you can think about it. And we have one pulse laser welding system beyond using that continuous wave fiber system based on NDOG. And you can look at that power. It's not 3000, but we have a 300 watts pulsed up to 20 millisecond. You can vary the frequency, also vary from 0.1 to 100 hertz. And you can see here a small spot welding. You can create a small spot welding. Very good system for doing some kind of a minute low depth spot welding of any material, welding of jewelry or some other related component. And I can show some video that is we are doing a butt jointing. So likewise, you can do a spot welding. I hope you are hearing the audio also, right? Justice, you are getting the audio from the video also?
Hello, sir. Hello, sir.
Yeah. When I am playing the video, you are getting the audio also, right?
Sir, can you once again play the video? It's like stuck. No, sir, there is no sound.
There is no
The audio we are not getting it, sir.
You are not getting the audio?
No, sir, no, sir.
Audio should be there actually. Just as anything that we need to do when we are sharing the presentation?
Sir, actually it plays out from your speaker, I guess, sir. That's why it is coming out.
No, in Teams, there is a play with audio, there is one option is there, but I am not sure. Just a moment.
Sir, if you have any speaker, if it plays via the
I
speaker,
don't have a
we'll get
speaker.
back to you.
Right, just a moment. I will share again to look at whether you are hearing the audio now.
Yes, sir. Yes, sir. We are getting the audio.
You are getting the audio now?
Yes, sir, it's audible.
Yeah, fine. Okay. Good. So, laser micro machining. So these are some of the application where we do a lot of interesting micro machining related activity, micro channeling, micro grooving, micro texturing, in order to alter the surface responses to different material, different requirement. And generally, if you have a hydrophobic surface, you can make it as a hydrophilic, or if you have a hydrophilic surface, you can convert into hydrophobic by appropriately changing the contact angle with the material that is coming in contact. And laser surface texturing is one kind of application we are extensively using for to realize some kind of tribo property improvement, like in a case of fins. These are all very, very small dimensions that is running into few micrometer, and you can get into any kind of a pyramid or a straight fin in order to realize the improvement in tribo performance, as you are literally reducing the contact angle, contact surface, the real area of contact by which you can do enormous improvement in terms of surface characteristics. And this is one of our recent addition, femtosecond laser based micro machining system. And this is a unique system available in southern part of India, where you can get a 350 femtosecond laser coming out of that energy beam. And this is one of the unique process what we have done to create a kind of conical holes with the entry diameter of close to 1 mm and exit diameter of 200 micrometer. And you can vary the frequency to several level from a single shot to 1 megahertz. And one such operation, what you can see here. So multiple intensity at different depths to create a conical hole that is possible. It is completely on the other side of, and this is one of our production faculty also working. Started working on laser systems, and this is again a recent addition. Laser marking, it's a high level accurate marking that you can do with this laser, and you can see that your barcodes being marked using that one. And this is one project what we have done for turbine industry, GTRE, not GTRE, it's for DRDL. laser surface texturing to improve the adhesion strength. And so we are doing different forms of laser surface treatment to improve the adhesion strength of the TBCs what is to be coated over that material. So previously they are using grid blasting to make the surface rougher and then they are coating, but we have proposed an alternative that this laser based texturing, a controlled removal of the material in order to improve the roughness. That would be really helpful. It's not very visible. You can see here it is around 15 micrometer. This is 90 to 116 micrometers. So you can look at the enormous increase in the surface textured roughness, which provided a very good improvement in the capability of holding the TBCs to quite long time, and from the serviceability part of improvement of service life, this is quite useful. And with that femtosecond laser, what are the possible projects that you can think about is microstructuring. I am not talking about optical microstructures. It is the structures what you can create in a micro level, and even we started working on different micro channeling applications, microfluidic devices. Either silicon scribing is possible, or a tissue ablation and micro nanosurgery, again surface texturing, thermal writing of photonic devices using in glass or polymer, femtosecond laser induced periodic surface structure. Already we have done some work on this. LIPS, it's called LIPS, and by which you can alter the reflectivity of the material or absorptivity of the material, and we have worked on this particular topic on a silicon wafer, and medical nano robots, what is the design, application, future challenges, and laser surface modification of polymeric surfaces for microbiological applications. You can think about any kind of an application, how that modification could be helpful in improving that one. Then manufacturing and characterization of water repellent surfaces, texture metal surfaces to make them more antimicrobial. You can use some kind of a material and texturing to cleaning some kind of a germs what's present, or a bacteria, to kill the bacteria. You can design some kind of a system, or a micro nano fabrication for energy devices. That is again interesting, a topic that is improving, and green energy harvesting and other related, where this laser micro machining is played a pivotal role in doing that one. And this laser shock peening, it is more of improving the fatigue property of a material or a fretting resistance of the material. For that also we have a very unique system for shock peening, and this is a 3.5 joule with a 10 hertz laser. And basically shock peening, it is can be realized by constricting the evaporation of the laser exposed material using a water column, that lead to putting some kind of compressive residual stresses inside the material. That would be helpful in improving the fatigue property or the cyclic loading. And for many of the turbine industries, we do this kind of shock peening over the surface of the material, which really helps in improving the fatigue resistance. And this system is very recently installed, and we started working on some of the fatigue related studies on different material. And this is for one of the industries, bearing industry in Jaipur, who started doing some kind of a consultancy using this system. And this is one video how the shock peening is happening, that you can look at it. So the laser pulses falls on a material on a very high intensity, and the 3.5 joule, you can look at the frequency. It is varying between 1 to 10 hertz. If I am reducing the frequency and in a lower or a smaller diameter, I will be getting energy density in gigawatts. So such a energy density definitely will induce lot of CRS, that is compressive residual stresses, inside the material, by which you can realize a very good improvement in fatigue property. So what are the possible projects that you can work on? Improvement of fatigue property and fretting wear resistance of machinery parts, orthopedic implants, gas turbine blade roots, laser shock peening on welded joints. One of the PhD students of mine is working on this one. And improvement of stress corrosion cracking resistance on biomedical implant, and treating selective laser melting components. That's again, we have a SLM system, and when you're doing SLM, layer by layer buildup of the material, generally has TRS, that is tensile residual stresses. So they do this laser shock peening to nullify the compressive residual stress, TRS, what has been in that system. It's a kind of annealing that you can try. So finally, in the additive manufacturing area, just we started working on as we get a very good metal AM system, and among these different classification, laser based additive manufacturing, it is inevitable, even though that electron beam additive manufacturing is coming slowly into the market. And if you talk about any powder based system, the laser, without laser you cannot realize that kind of a buildup of the component. Either it's selective laser sintering or selective laser melting, and you can extensively think about using laser. And the SLM based process, we have one laser system, that is laser powder bed fusion, or PBF system, where layer by layer you can build up the material. The starting precursor material is in the form of a powder, and it is spread across the table, and selectively where you wanted to build the component, it will get melted and then solidified, and then the platform is lowered one layer down, and again the laser is melting, and continuously you repeat the process to realize the final component, which is one of the highly commercialized process in the recent times. And the direct metal deposition, already I have told about what laser cladding, how the laser cladding been extended for this kind of additive manufacturing system. And some of the applications where you can think about doing your project in these defense applications. You know, the aerospace, you have quite interesting components being developed by a lot of leading manufacturers. For example, GE has come out with one fuel nozzle using AM, and through that they reduce the number of components present in that fuel nozzle. And when you say that, when you have a more number of components, and the reliability will come down naturally, as the chances of failure will be very high. So generally when you talk about AM, one thing many has an objective to go for a light weighting, so reduce the weight. How to reduce the weight? By optimizing the structure. The second one is parts consolidation. In conventional manufacturing, you are unable to consolidate the parts because of the manufacturing intricacies or a difficulty in doing that one. But here they have reduced the number of parts and consolidated into a minimum level, by which the durability has increased several fold, up to 5 times. This is one of the excellent example of the additive manufacturing, why it is providing a better futuristic technological requirement. And here 3D printed parts for aero engine, different parts they have printed with some lattice structure, all those things, and entire combustor is being built. And G also proved they have built the complete working turbines using a 3D printing technology or additive manufacturing technology. And this is again one example of classic example of light weighting, as 63% lighter than normal component that they have produced without sacrificing the functional requirement. And this particular firm started producing turbine blades with a cooling hole imprinted on it, which is very, very complicated when you talk about if you are doing with a conventional process where micro EDM drilling that they are using. Again, there is a limitation of producing curved holes. But here in this case, you can produce a curved hole. When you talk about medical application, a lot of orthopedic implants, dental implants, 3D printed cortex cast. Cortex cast, earlier you use a plaster of Paris, which is very not appealing, and you get a lot of itching when you supposed to wear this for 2 or 3 weeks time. But without losing the strength, you can create this kind of a cortex cord and some kind of implants and other related devices that you can create for a medical application. And transportation, this shuttle Oli, it's a classic example of complete 3D printed e-bus, electric bus, a small minibus where all the components are printed using 3D printing technology. Even for small batch production, you can think about using 3D printing. An entire engine casing can be built, the front shielding and this kind of chassis, and the entire chassis of the bike also can be built using 3D printing. And what is the system available in NIT Trichy? And this is a very good system with a commercial build capability of 500 by 250 by 250 which is quite big volume printing. And also we have a twin laser system by which the productivity is entirely doubled, and you can vary the powder thickness from 20 micron to 100 micron, and a very good accuracy that you can get. And we just started using this printer, and it is having a very good capability of doing multiple material printing. But we started with stainless steel right now, and you can feed the powder here, and the powder goes here inside the build chamber, and you have a requarter system which will spread the powder on the build plate, and you have a twin laser here which will come here to melt the material, and the build chamber will have a table by which it will move down layer by layer every time when you are building, and the entire process can be controlled and monitored. And right now we have the parameter for these different material: aluminum alloy, steel, titanium, nickel. And right now we are concentrating on 316L stainless steel. If any of you have a requirement, possibly we can do that one. This is the setup of the 3D printer. And we have other auxiliary systems also. This is the vacuum conveyor, powder sieving. And on the other side we have some other accessories to reclaim the used powder. And this video shows how layer by layer the recorder is spreading the material, and what you are seeing here, the laser is melting one of the layer what is been already laid, and then you can see that the recorder is coming, the build bed has gone down, and then it is putting one more layer over that material. And what is that you are seeing here? It is depth of the build layer or the build plate that is gone into that one. So what is literally mean that below that you have some material that is already got built inside, and possibly when you look at that after completing the build, and what you have seen in that video, actually the system is building this particular component, and after removing the powder, probably you can see layer by layer how it is being built. And we also tried without any support in a 45-degree inclination how we can build. And this is also additive manufactured in our laboratory. It's a classical lattice structure with a lightweight and some of the cylinders, and this is one complicated gear with some kind of a support that we have built very recently. And what are the possible projects that you can work with that? Lattice structure based designs are quite appealing for any kind of catalysts or some kind of functional applications where you are looking for some kind of lightweight or improved strength. You can come out with some kind of a novel lattice structures that can be printed, which is otherwise not possible with conventional systems. And printing orthopedic or dental implants, printing parts used in any automobile, aerospace, printing drone parts, printing tiny assembled robots, kitchen and bath fitting. Quite a lot of interesting things are coming in. and surgical instrument that you can print using this system, where the surgeons are always looking for some kind of improved design which has some manufacturing limitations when you try with conventional systems, which that you can do it here. And functionally graded using 3D printing, or use of pulse laser welding for MEMS packaging applications when you talk about the pulsed 3D printing of jewelry parts, sustainable 3D printing of complex shaped forming equipment. You can even target agricultural sector, or a multifunctional components such as integrated electronics and sensors in AM process, which is highly possible using this 3D printing techniques. Just I am summarizing what are the different laser facilities with the different power and pulsing combinations, which is very unique, that you cannot look in other systems, where when you look at here, and also I have indicated the cost, because when you go with a higher power or lower pulse width, the cost is enormous. And if you are generally going with a 300 watts with a 20 milliseconds, obviously you can get a reasonable frequency, you can get it laser at a cheaper rate. But when you are going with a higher power, 3000 watts, then the cost is a little higher, 3 crores. And a femtosecond, getting that in 10 power minus 12th of the second, one pulse, it's quite enormous. Sorry, 10 power minus 15th of the second, you get it at the cost of a 1 crore. And you look at the combination, this is 3000 watts, 300 watts and only 40 watts. But this is mostly or predominantly that we are using for continuous wave. And in the case of a pulsed, it is millisecond, but it is going into femtosecond. And the frequency also, that's a huge variation. Here you get, if you are modulating that continuous wave beam, you get into 1 to 15 kilohertz, but you are going in only hertz up to 100, and you can go up to megahertz here. And the laser marking system, you are getting the pulses in nanosecond, and again in the range of 30 to 60 kilohertz, and the laser power at 30 watts. And here you can look at carefully that the frequency is only in 1 to 10 hertz, so that you can get a higher energy density. And this metal additive manufacturing as a whole, it costed around 5 crores, and I am not including any pulsing, because it's a continuous wave fiber laser, twin laser that is going in operation. Beyond that, we have other supporting facility like high temperature indentation tester. Normally you do harness at a room temperature, but here we have the possibility to characterize the material at a high temperature. And we have sorry, here the name got interchanged. It's a white light interferometer, and we have one wire cut EDM also. So most of these laser systems are equipped, some in OJAS, some in this manufacturing COE. And if you wanted to get more information about other available facility, you can visit the manufacturing COE, Elliott Siemens COE, visiting this website. So within that, you can also look at our center detail, Center for Advanced Manufacturing and Automation. And using those systems, we came out with a spin-off company, InventGlow Technology Solutions Private Limited. It's a startup company promoted by me. And through that, we are catering to different design, material printing needs of industrial clients. And this is the overall activity of that laser based facilities, as well as the research projects and possible scope of working with lasers that I have given right now in this short presentation. Hope I am well within the time. So thank you very much for the research forum for giving me an opportunity. If you have any questions, probably you can ask me, or otherwise we'll close the session. Thank you.